Hi, my name is Anthony Spradling, and this is my Lab 3 physics submission for Physics 2211. The purpose of this lab was to construct a computational model in GlowScript to track the motion of a sun orbiting a black hole and to track the motion of a spaceship orbiting a sun and moon in order to get a better understanding of gravity and Newton's second law. The fundamental physics principles used were gravitational forces, Newton's second law, centripetal forces, and net force. In the end, we were able to find the mass of the black hole by iterating the motion of the star around it, but we were unable to find a trajectory for the spaceship such that it wouldn't crash into the moon when orbiting. Some of the main physics ideas were the fundamental gravity forces, position update formula, F-net parallel, and perpendicular. We use these principles to calculate new positions and velocities in both scenarios and update them over time to get a better understanding of what was going on in the system as a whole. For part 1 of the lab, when the sun's orbiting the black hole, we define the system as a black hole and the surroundings as a star. For the computational model of part 1, the most important parts are highlighted with arrows. These include the initial velocity conditions, initial momentum conditions, and net forces in the parallel and perpendicular direction. In order to calculate the mass of the black hole in each iteration, we first had to set up an equation with all the balance forces, and then isolate the mass of the black hole. After doing this, we get the equation at the bottom. In the end, we found that the mass of the black hole to be 1.0554 times 10 to the 44. Here we have the computational model for part 2. The most important parts were finding the net forces for the ship and the net forces for the moon. To get these, we had to compute each force individually. We first set up the equations to solve for the force of the planet on the moon, the force of the ship on the moon, the force of the planet on the ship, and the force of the moon on the ship. By combining these forces, we were able to iterate the position and velocity of both the ship and the moon. We then had to do some guess and check work to find what the initial conditions would lead to with the motion that we were looking for. In the end, I was not able to find the initial conditions that would satisfy the infinity motion, but the steps to getting there was still an important part of the process. Some possible sources of error from these experiments was that we assumed that there were no external forces. We also used iteration steps to find the new positions, and in doing this, we never get a 100% accurate description of the model. The smaller the iteration steps, the more accurate we can get, but there's always going to be some degree of wrongness due to the nature of the process. We also could have some issues with the initial velocity of the ship in the second experiment that could lead to some inaccuracies. So the reason the net force in its parallel and perpendicular components were different from the rate of change of momentum in its parallel and perpendicular components was that the momentum has to do with the direction of the velocity, while net force works solely with forces instead of motion. If the system had a black hole, star, planet, and moon, and we wanted to predict the motion of the entire system, we would need to include how each object affected the motion of other objects based on the forces. For example, we have to say that the black hole applies the forces on the star, planet, and moon, and the star applies forces on the black hole, planet, and moon. These forces would change the position of the objects in the system, and thus the gravitational forces would constantly be changing based on the changing r, or the changing radius. This would be a very complicated model, but it would be simple to break it down into each piece. The most dominant of forces and changes to position would come from places in the system where there are large differences in the mass between the mass of the two objects and small differences in the displacement between the two. Like if a small moon were pulled by a black hole that was very close to it, its change in position and velocity would be much larger than a black hole and a star that were very far apart. That's the end of my lab. Thank you.